Today we are going to study about lattice vibrations, and it is the first part of thermal conductivity lecture. So if you draw potential with respect to x for two atom system, it means that one atom is brought near the other atom. Then you see that the potential is first, it will be attractive and then it will be repulsive. So this point where the minimum potential energy is there, it is called the equilibrium point. And if you write an expression for this potential, it is actually given by, because this part is parabolic, so it will be half kx squared. And if you take first derivative of this potential, you know that negative derivative of potential is given by force. So you can get here minus kx. So this shows that the force between two atoms will be like a linear spring, as if they are attached by a linear spring. So we have also found out that if a mass is attached to a spring in a spring mass system, the frequency of oscillation is given by this expression, which it is nothing but by Newton's second law of motion. You can very easily find this by the simple calculation. And we also found out that in a harmonic oscillator, that the energy is quantized. So if you have an oscillator, its energy will always be quantized, and the energy will be added as n will increase by a factor of hf, while the ground state energy when n will be equal to 0 will be given by half hf. So let us assume that we have a linear chain of atoms, and let us say that we are talking about this particular atom and they are oscillating with respect to each other. So they are vibrating with respect to each other. Let us try to find out what will be the amount of force that will be acting on this atom I due to the atom I minus 1 and atom I plus 1. So I is just the number that we are giving just to make the problem easier. So U is what we are assuming to the displacement of the atom, and X will be the coordinate of the atom. So here I have missed it, but Ui actually will be Xi minus X naught. So coordinate for the equilibrium and coordinate when it is displaced. So the net displacement will be given by Ui for the ith atom. So and Xi will be denoted by Ia, and A here is the interatomic distance, and I because the number of atom that we are talking about. So if you have to find out the total amount of force acting on this ith atom, we are using Newton's second law, so it will be mass of that atom and double derivative of the displacement, and the total displacement will be the total force will be minus k into x. So x will be actually the total displacement. The total displacement on this one will be the displacement due to I plus 1 minus ui, and because of I minus 1. So this will be the total displacement. So now let us assume that this is the solution for this equation, and let us put this equation solution into this equation. Let's see what comes. So here I have denoted I by j, because we are already using the notation I here. So when we take second derivative of d square of u, this is what we get. So let me just write it as ui. Okay, so if I write it as ui, then x will have to replace by ia. So that will do in the next step. So you can take k outside, and this is what your equation becomes. Okay, so let us calculate the right hand side of the equation, and we'll see that ui plus 1 can be given by I plus 1a, and if it is I, then it will be ia. If I minus 1, then x will be I minus 1a. So putting all these equations, taking this term constant, we are left with this. And now we can put all of them in equation 1, where it will be the left hand side, and this is the right hand side of the equation. So here these terms cancel, and you're left with this. And you know that this factor and this factor turns out to be 2 cos ka minus 2 factors here, so it comes here. So by this simple calculation, we come to know that the frequency will be actually a function of sinusoidal function. And because in most of our discussion I have usually depicted omega by f, so let us keep it as f, which is nothing but the frequency of oscillation of the atoms. So now if we plot this equation, we see that it will look something like this. and it will have its maximas when sin Ka upon 2 is equal to 1. So Ka upon 2 will be pi upon 2. So from plus and minus direction, you'll see that K will be maximum at plus minus pi upon 2, and this is how it will look like. So you'll see that in most of your books, usually the dispersion, this is the dispersion relation actually, because it is a relation between frequency and K, wave vector K, that is why. So in most of the books you'll see that only this part of the spectra, only this part of this is usually taken, because it will be periodic and it is symmetric, so you need not take other Brillouin zones. Okay, so this relation we'll be using in the next part, so that is why we've discussed this relation first, and we'll discuss a little bit more about it in the next part.